So I hope everyone is doing well and staying safe.
Yes, thank you.
The U.S. has had broken records in the number of COVID cases,
Mm,
highest highest daily record since August. So,
mm, wow.
um, let me screen share, and I'll kind of have to do some of this in real time. I got up a little later than I wanted to this morning. Okay. All right. So go here. And screen share. I want to talk a little bit about time. Uh, in particular, I want to observe that um, the calm rule in the pi calculus is effectively instantaneous. Or sometimes we can think of it as taking a unit of time. And the same is true in the ordinary rho-calculus. So in the ordinary rho-calculus, we have a simple calm rule. And we can think of synchronization and transference of data as either instantaneous, i.e. taking no time, or it takes a unit of time. We consider time having marched forward for those two processes by one unit. Notice that, of course, you now get a not a global notion of time, but a local notion of time. So it marches forward for the forecomprehension and the send, but it doesn't march forward for anything they might be in par with. So that's a local notion of time versus a global notion of time. And I want to compare that. So like we know that there are some processes that that do take time, right? They require um, they're more durable. They have a duration, and there are steps in the process that have a duration. And so, is there a bridge between sort of instantaneous communication and duration? So that's a question that I think is interesting when we think about the computational world modeling the physical world. And I just want to point out that we have that built in to the notion of annihilation. So if you recall, we say that two processes, S and T, annihilate each other, which we write S perpendicular to T. So when S is perpendicular to T, if whenever S evolves through some number of steps to R, that implies that R evolves through some number of steps to 0. So it means all paths out of S par T eventually end up at 0. Is that clear? Does that definition make sense to everyone?
Yeah, it makes sense to me.
Okay. So then what we're saying is that the COM rule says we no longer have that it's the same name the source is sending on and the target is receiving on, but rather when you put the processes that those two names quote in parallel, that they annihilate each other. So that's the basic idea. So now we can say that if it's at 0, then it's either a unit of time. Notice that 0 annihilates itself, right? So then that could be a unit of time or instantaneous, depending on your choice. But then we can look at annihilation in terms of a duration. And we can say that that duration is somehow a weighted average of the path length from s par t to 0. So you look at all the paths. So this is starting to look remarkably like the Feynman integral, right? So you're looking at all the paths from s par t to 0, and you take some kind of weighted average of the path lengths, and that gives you a notion of duration for this communication. Does that make sense?
So you're talking about all the possible execution paths, not the specific one.
All the possible executed. I'll take every single execution path. We know that every execution path ends in 0. So we know that between s par t and 0, there are a bunch of execution paths, and in fact, all paths originating in s par t eventually go to 0 by definition. And so now we look at all of the paths and we take a weighted average of their length. Now, yeah, so now where do the weights come from? And this is where things get very interesting. So if you recall, I also gave a definition from the quantum mechanics of the following. So we have the transpose of P is P par whole, right? That's the definition. Okay, and then we define the probability amplitude as the transpose of P star Q, which is just the application of this context to that process. Right? So now what we can do is, instead of demanding that annihilation, that they perfectly annihilate each other, what we can do is to look at the probabilities of we can look at the probabilities of the of transpose of S applied to T. So let's just double check that everyone understands what I'm saying. So when I say transpose of S applied to T, what do I mean? I need to go here. Should be in favorites. Of course not. Oops. All right. Now we want to go format, font, baseline, superscript. Okay, there we go. All right, so this is defined to be essentially the application of, oops, S par, of course, I have to put in the box. So it's the application of this thing. Lord have mercy. Okay, there we are. So we're going to apply that context to that process. Right? And that is just equal to S par T. Wow. Incredible. Okay, so that's what I mean when I say that, right? That should be clear, right? And now, remember that we define S T to be that. And so this is all, right? And so now what we want to do, so this is in fact going to give us a probability. It's going to give us the square root of the probability. So what we want to say is that the probability of making this transition, so the probability of making this communication happen is given by this, the square root of the probability is given by this. So in other words, it's this thing squared. So the probability of making this transition is this thing squared. Is that making sense?
Yeah. This is some kind of distance to complete reduction between.
Well, what we're now saying is we're giving weights. We're giving weights. So instead of making it all paths, right? We can give the weight. We can give the weight of the interaction, and the weight of the interaction. So now if you have race conditions, right? So you have another, say another X source prime or X prime sub S par Q prime in a par with the forecomprehension located at X sub target, X sub T. then the probability of that one is going to be the square of the inner product of S prime par T, right? So now you can look at the different weights. So the point is that we can get now both a notion of duration and a notion of likelihood. Are you following me?
Yes. So we get some. This weight is on the specific paths.
No. It's not on a specific path. What we're saying is that we're actually representing the weight as a particular process, right? And that weight corresponds to what we did with annihilation. So annihilation. So we pick only processes that annihilate each other. So we know that all paths out of here will end in a zero. Does that make sense?
Mm-hmm. Yes, yes.
Right? And we know that we can take an average of the path length. But now we want to understand what would a weighted path be. So now what we can say is the weight of any single transition is given by its probability. Right? So a single transition, like this one here, is going to be, if we take it, it's going, as opposed to taking some other transition that might come out of, some race condition. The weight is given by this thing. Does that make sense?
When you say this thing, you mean like starting point.
So let me. It's very difficult to do omnigraphal in real time with this particular set of. Move this over. Move this over. That's still visible to you guys, right?
Yes, yes.
Okay. So the idea is that the probability of making this particular transition as opposed to another in some race condition where this expression is a sub-expression. So we have some expression as an example. So let me grab this one.
So we can have multiple possible com-events.
Yes.
And we can see and there are like different paths that we can choose to go to annihilation.
Yeah, so perhaps the best notation would be something like this. So here, we're going to decorate this with a probability. So it doesn't just go, it goes with a probability, right? And so let's call that, yeah, I've got it now. We'll call that phi of ST. Here we go. I can grab it from here. I'll just get this much.
Can I ask you about annihilation? When you say this will end up with R and R will end up zero. from one point, this can be true. We can have all of the processes, and we can see these paths that are going to zero. But after first COM event, the situation can change after just one step.
Uh-huh.
So how we are we then recalculating our probabilities, or because then some paths maybe are not possible anymore because, or no, you said that all paths will ends up to zero. So there must be.
Yes, all paths. That's the definition. Yeah. What happened here? Why did it do that? Okay, there we go. All right. So here's my notation. I think this will make it clearer. Okay. So what we're saying is the weight of this particular transition here. So we're going to make the transition with this weight or probability, and I'm going to define that to be
And when you say make a transition, you mean complete transition until zero?
No, it's making a single transition.
Okay.
Right. So format font, baseline raise. No, that's not it. Okay, fine. I'll just do the whole thing over again.
But with each step, we are reducing number of paths, and in that sense, probability, right? Because we are closer to zero.
No. So there are two different paths, right? There's this expression, and there's this expression. We're trying to evaluate this expression, right? In order to evaluate this expression, we evaluate this expression. And then recursively the same, right? So if this has a reduction in it, we need to evaluate that one. So we'll have to go and find the xt and the xs in that one, and so forth until we get all the way down to an at zero with an at zero. Does that make sense?
Yes. So basically, with this execution of these COM events can create a new paths, and it can also expand probabilities or possible paths.
Not sure. Oops.
Let me explain it how I understand it to this point. So we have the multiple paths. All paths are trying to go to zero. And as in each path, you have these calculations. Some are short, some are long, but that's immaterial. It's the probability, the chance that you'll be able to do a calculation that progresses you further along in this path to ultimately get to zero. So the chances of this transition, or the chance of doing a calculation to further you along in a path, gives you greater weight to that particular path. So the path that has the greatest chance of ultimately reaching zero has the greater weight.
I didn't say that. What I was saying was that the probability of a given step, right? So you multiply the probabilities along each step.
Right. So each step in this, or the transition, has a probability.
Right, and then and then from so you think about it. Maybe if I draw a tree, you'll get what I'm saying.
Probably didn't say it correctly, but I think I'm getting the general idea.
Yeah. So we've got some P and some Q, right, and we know that some transition out of P and Q. So let me do that. so. Okay, so I have a P and a Q. Grab it from here. So I have a P par, I have a P par Q. And we know that it's P par Q, right? Because that's the only thing that will actually have a path out of it, right? Nothing else reduces. Only P par Qs reduce, right? So this is the top of some process graph, right? And we know that that's going to have potentially many different children, right? And we know that if they're going to have paths out of them, they're also par expressions. We don't know where the P, like the P prime could have come from. It didn't necessarily come from P, right? It could have come from somewhere else. And this is, you know, double prime and double prime. Right? And then this one is, we don't know how many primes there are.
But we see all of this from the root P and P par Q. Because we know that they are annihilated to zero, so we know all of this.
No, P and Q don't annihilate to zero. No. Along, they don't annihilate to zero. That's the point. That's where I think there's a confusion, right? So let's go to stencils. So we'll get this one.
What I was thinking, we know that this is one step in this process of going to zero.
P and Q do not go to zero. We know that a step out of P and Q has to look like one of these things, right? So inside P, we have something that looks like this, or inside Q, we have something that looks like this, or across the PQ boundary. So I'm going to change this not to a P, but say, I don't know, a G and an H. Okay, so there's a G and there's an H. Okay, and that's going to go to a G, right? And that's going to go, that's going to be an H. Okay, so somewhere inside P, there's something that looks like this, or inside Q, there's something that looks like this, or inside P is something that looks like this part, and inside Q is something that looks like this part, or the other way around. Does that make sense?
Okay, yes.
Okay, and now, in order for this to happen, we know that these things have to annihilate. It's not the P and Q annihilate. It's that the source and the targets of this particular interaction have to annihilate. Does that make sense?
Yes.
Okay. Okay. So that's the whole idea. And now what we're saying is the weight of this particular step is given by phi, right? And that phi is defined to be this, right? Where this is defined to be that, right? So we can now integrate. We can get both probabilities and we can get duration, right? So we have a quantum mechanical like evolution of our processes, and we know how much time they take. So that to me is quite interesting, right? This is a very, very different picture of communication than you see in the pi calculus, right? So we have a notion of instantaneous or unit time. We have a notion of a communication that has a duration, and we have a notion of the probability of taking a step in that communication. So this is very, very different than what's in the pi calculus.
So our reduction of P and Q will produce whatever is needed for xt and xs to annihilate each other with some number of steps.
I don't know how to interpret your language. So in order to go from here to here, right? In order for this thing, so we know that if this process reduces at all, it has to look like this. Are we in agreement there?
Yeah.
Okay, good. And then in order, and when it looks like this, in order to apply the COM rule at all, either entirely inside P, we find a process that looks like this, or entirely inside Q, we find a process that looks like this, or one of the components of this par lives inside P, and the other component of this par lives inside Q.
And in the first example, when everything is on one side, we don't basically need this another. If everything is in P, then Q is not necessary.
Right. So in that particular case, we have a P prime par Q.
Mm-hmm. Okay, I see.
Yeah. So
we can still do the reductions, right?
Yeah. Right. I mean that's the right. That's what the meaning of par is. That yes. Does that make sense?
Mm-hmm. Yes.
Yeah. Yeah. Cool. All right. So then right. So the interesting point is that to make a step like this, you're going to have another graph like this one, but for xt and xs. Right. Right. And then in order for any that graph, right, you're going to have another graph for some other x prime t and x prime s, right, for any one of the steps in the graph for x and xt and xs, right, until you get down to at 0 and at 0.
Does that make sense?
Yeah, cool. And now the thing that I didn't talk about in the original row paper is the weight, the probability of any one of those transitions. And now we can use these definitions to calculate probabilities. So the probability of making this step is given by the square of this thing, because this is defined to be the square. You know, this thing is the probability amplitude, or the square root of the probability. So you square this to get the probability of making this transition. So everything is inside the rho-calculus. Weighted transitions, durations, all of it is sitting inside this notion of annihilation. To me, this is quite remarkable. This is a very, very different calculus. Anyway, that's all I got. That's I just think this is really quite intriguing, right? Because we get a notion of we have a clear notion of instantaneous or unit time communication, and we have a clear notion of communication that takes time. So we're finding a connection, like the problem with with the Newtonian or sort of the views of interaction that are built on Newton's calculus is that time is on the outside. Time is a parameter to the system. It's not on the inside. And so what that does is that gives you this tension between what is instant, right? And what is and what has duration. And you see this, right? It's like it's even difficult to connect different scales, right? We can't connect these scales. Like you have differential equations that govern what happens in the nucleus of a cell, and those things happen, in minutes. And you have things that happen in the cytoplasm, differential equations that govern what happens in the cytoplasm. And those things happen in like femtoseconds. It's really, really fast, right? So relating the two timescales, because it turns out that the events that happen in the cytoplasm impinge upon the events that happen in the nucleus. In particular, when a single cell, organism with a flagellum encounters a sugar, it will rotate the flagellum to follow the trail of sugar, right? So that's something that we can observe with a microscope. Now, the sugar is impinging on the surface of the cell, which is then communicating chemical events through the cytoplasm to the nucleus. And the nucleus is producing proteins which rotate the flagellum. So the communication events through the cytoplasm are happening at lightning speed. They're virtually undetectable by comparison to the time scales in the nucleus. But when you try to write down the bridge between those two time scales in differential equations, things blow up. This is a well understood problem in the it's very difficult to manage. Nobody has a compelling answer to this, at least the last time I looked at the literature, which is about 10 years ago. So maybe in the intervening time someone found something, but at least in the kind of 2010 time frame, this issue of time scale was completely mystifying. It was technically difficult, very difficult. Now here, what we're talking about is a bridge, because the time is on the inside of the system, not on the outside. Right? And this is what I've been trying to talk about. It's very, it's a profound difference, the shift that happened with the lambda calculus, and then continued with the pi calculus and with the rho-calculus. The shift is, classical mathematics, which looks at things like, magmas, monoids, groups, rings, fields, vector spaces, modules, et cetera, et cetera, et cetera. All of those things, they sit there. There's no behavior in the data structure. The behavior is in the morphisms between those gadgets, right? So in the functions that take one vector space to another, right? That's where the behavior is modeled. In the lambda calculus, that's not. So when you specify a category of vector spaces the objects are the vector spaces, and the morphisms are the transforms that preserve the linear, the vector spaces. Right. So that's your category, and that's what people use to investigate vector spaces in this day and age. But that's not how things are packaged in the lambda calculus or the pi calculus or the rho-calculus or the ambient calculus or the blue calculus, yada, yada, yada. In those models of compute, which are compositional, what you have is a term language, like the lambda terms or the rho terms, some structural equivalence, which is whacking those terms down to equivalence classes. So there are syntactic differences that don't make a difference in terms of behavior, and some rewrite rules. And that's a part they're all packaged together in a single structure. So if you want to talk about a category of lambda calculi, you have to include, or even better, if you want to talk about a category of these different kinds of systems, so the systems would have a lambda and a rho and a pi and an ambient. They're all sitting together in one category. And now, if you were going to have morphisms between them, you have to talk about the morphisms that preserve the rewrite capabilities. What does that mean? Right? Nobody has a good answer to that. Even Robin didn't answer that with his bigraphs. We don't have a good notion of what that is. Now, you might be able to come up with one, but so far no one has come up with that. But the point is that by packaging the rewrite system together with, in the rewrite rules in the whole system, time is on the inside of the system rather than on the outside of the system. It's not a parameter. It's built in. And that changes everything. So that's why this is important. That's why, this is because it's a very different packaging of our notion of what dynamics is. And if you think about it, there's a kind of, what I'm saying is very similar to what physicists have been saying about string theory. So, physicists like Lee Smolin and Sabine, I can't think of her. Yeah. I'm not sure. Yeah. So these characters are all pointing out that, we've had this, string theory has dominated the physics departments for decades without providing experimental guidance. So it might be interesting mathematics, but it's not physics because it's not providing experimental guidance. And so we need to look at that, the hegemony of string theory in a skeptical light and say, hey, no, that's not cool. We're not doing, it's fine to do math, but don't do that in the physics department. Physics needs to ultimately result in guidance for experiment. And I'm saying, no, it goes further back than that. It's not just string theory. You have allowed Newton's framework to have this grip on how we model dynamics that has consequences, and there are grave consequences. In particular, it is now a central problem of physics to relate quantum mechanics to gravitation. And I want to argue that's because time has been put on the outside of the system rather than on the inside of the way we model dynamics. And I'm here with this little tiny idea. What I'm showing, what I'm demonstrating is a system where the dynamics models the full range, right? So we have instantaneous or unit time together with duration, together with weighted paths. all of those things show up in a system where time has been packaged on the inside. So that's the significance of a point like this. The cultural significance is, hey, I think we can do a lot better. Here's, there's probably umpteen dozen things wrong with what I'm doing here, but it deserves the attention of the scientific community to come and help me fix it. or say why you could never ever make this work, right? That would be a fantastic result. I would love to see that. But we know up to here, this is all solid. This is all mathematically solid. Now, the point is that when I'm giving probabilities here, they're not probabilities in terms of the real numbers. They're probabilities in terms of a different algebraic system, which I gave here, right? So I've given the algebraic system here. Now, people may want to say, okay, well, that's not sufficiently close to a notion of probabilities to carry out quantum mechanics, and they may be right. But it's certainly worth the discussion, right? And in the middle of that discussion, some bright person may come along and say, that doesn't work, but here's a variation that will. Right? So that's but everything up to that point is 100% solid, right? And there are ways to just, right, there are already notions of stochastic process algebras which don't depend upon this particular notion of probability. So we could put a weighted step here that is calculated in terms of these two processes, right? So that would be that's also it's possible to work out that machinery as well and not have to rely upon the one piece where there might be questions. So you can take something that's more established and slot it into this particular notion of weight, and it will still work. So the whole system, because it's compositional, is modular, right? So it's much more robust than it might appear. So I feel like that's why this is of significant value. Yeah. I guess I should shut up now. I'm just rambling. Any questions?
For me, this very much makes sense because if we have a time somehow outside, and if we measure something, then if we later if we include more information, we cannot use the previous measurement because we have time outside, but in this model additional information will just give us a more precise probability. Is this make sense?
Yeah, exactly. Yeah,
yeah.
Go ahead.
It looks like very much more compositional than having some measurement or on the global time, which I'm not sure how can be compositional.
Yeah, exactly. And we know, I mean, like relativity tells us that this idea of local time is the only idea that makes sense. There are things that are space-like separated. So because they're space-like separated, there's no causal ordering. The events in a region that's space-like separated from another region are not causally ordered. So, and we have a way of modeling that in this framework, right? So the process P that has a bunch of free names on which communication happens, that all of those all of those events are time-like separated in the sense that there's a causal ordering, right? Because you can just look at the synchronization tree, the graph of all the executions, and you can get a clear a clear notion of what causes what, right? The COM events, the graph of COM events gives you the causal graph, the causal structure. Whereas if you have P par Q and there's no free names between P and Q, and there's no evolution of P which creates a name which is found in any of the evolutions of Q, and there's no evolution of Q which creates a name that's found in any of the evolutions of P, then we know that they are space-like separated. So we can model the notion of time-like and space-like separation in the process calculi, no problem. Not even breaking a sweat, not even hard. And physics, if you believe general relativity, then this is just a consequence of the model. You can't get away from that. So, it feels to me like that's a real another piece of the evidence that suggests that this is worthy of investigation, and it also shows that there is no global time. There's only ever local time.
How can we transition from our thinking in global time to local time, and what can we use that we already have?
Music. Music, but again, not the written music. Written scores are silly in this regard because there is a global clock, which is the smallest audible subdivision of the beat. Charles Ives looked at having two different orchestras that were, had different tempo, and pieces where the orchestras would, interact with each other, but they would be on different times. But if you listen to the music, especially the music of indigenous peoples, there isn't a clock. The music is situated in an environment, and that environment is, giving you a notion of the ebb and flow of time, right? And that's the same as, a process in which you have some number of free names which govern, what the causal structure. That's the idea. So if you go to Africa and you participate, for example, in the sabar drumming, you can, or the djembe sessions, any of that, you can hear as clear as a bell this different organization and perception of time.
But I mean, it's not just time that is missing in the classical math, right? The sense of location is also missing. The sense of movement of direction is missing. Both of those things are missing as a matter of basic defining something. So if you do requirements, a lot of times you run into problems because of that, because you're trying to attach location or sense of geography or sense of movement or speed, not just speed, but velocity of something as additional things to work out later. So I think there are, in some domains, there are requirements that capture all of that, the time, the location, and the velocity. But if you kind of take an attitude that says those are fundamental to everywhere and start implementing those, I think it'll become more natural. For example, you take something like a geographic address, right? And you have a physical building that has 10 floors. There are schemes now proposed to say, well, we should be able to include in the address, or when we think about the address, that it's a three-dimensional thing where, some number on apartment or floor number 9 is different from floor number 6 or whatever, or between, a door that's within this 1 meter or 2 meters is different. So it's just a matter of really being sensitive to, being thorough, I guess, in terms of how you think about physicality and making sure that you're capturing everything that is around that, which is both time, location, and velocity, in addition to what we're used to capturing, which is just the conceptual, but not the physical. So anyways.
Yeah, so I think what you're saying is you said time and space are not in classical mathematics. No, I think that they are in classical mathematics. They are. You don't find location well represented in Turing machines, right? And you don't find location well represented in lambda calculus. It's arguable that you find a good notion of location in ambient calculi. But how do I say this? The classical physical, when physics models dynamics, they do so in terms of metric spaces, right? So in fact, they do so in terms of very, very special forms of vector spaces, right? But the important thing about the vector spaces, so that vector spaces clearly model a notion of time, right? That's kind of the whole, and a notion of location. So the Minkowski space-time and sort of the whole idea of the metric there is very, very clear. But the problem is that the relationship between events and these space-times is overlaid. So when you look at it's 8 o'clock. This is a very interesting discussion. I guess all I'll say is typically what they do is they hypothesize a chart structure, so you can overlay these vector space like grids over top of some topological manifold of events, right? So the manifold is giving you the what we call the interactions, right? The significant events, and the metric space is giving you their location in space time. So they're separated, like how the manifold overlays, or how the vector spaces overlay on top of that manifold of events is unspecified. It's just that whatever structure you use, when you have an overlap, you have to have differentiability in the overlap. What computing says is, no, here's how they are related. The events give rise to the space-time in a particular way. That's the difference. All right, see you folks in the Dev Stand-Up channel. Thanks for the interesting conversation.
Yeah, thank you, Greg.
Thanks. See you.
Ciao.